Hi everyone! Today we will learn about glycolysis. Glycolysis is the sequence of reactions that metabolizes one molecule of glucose to two molecules of pyruvate with the concomitant net production of two molecules of ATP. Pyruvate can be further processed anaerobically to lactate or ethanol. Under aerobic conditions, pyruvate can be completely oxidized to carbon dioxide, generating much more ATP. Glycolytic pathway is common to virtually all cells, both prokaryotic and eukaryotic. In eukaryotic cells, glycolysis takes place in the cytoplasm. This pathway can be divided into two stages. Stage 1 is the trapping and the preparation phase. No ATP is generated in this stage. In stage 2, ATP is harvested when the 3 carbon fragments are oxidized to pyruvate. This table summarizes the 10 reactions of glycolysis. The 10 steps of glycolysis can be described in terms of their substrates, products, and enzymatic mechanisms. The glycolytic enzymes catalyze phosphorylation reactions, isomerizations, carbon-carbon bond cleavage, and dehydration. ATP is consumed in steps 1 and 3, but regenerated in steps 7 and 10 for a net yield of 2 ATP per glucose. For each glucose, 2 NADH are produced in step 6. In the first stage of glycolysis, glucose is converted into fructose 1,6-bisphosphate in 3 steps: phosphorylation, isomerization, and the second phosphorylation reaction. The strategy of these initial steps is to trap the glucose in the cell and forms a compound that can be readily cleaved into phosphorylated 3 carbon units. Stage 1 is completed with the cleavage of the fructose 1,6-bisphosphate into 2 3-carbon fragments. These resulting 3 carbon units are readily interconvertible. Firstly, glucose enters the cells through specific transport proteins and has one principal fate. Glucose is phosphorylated by ATP to form glucose 6-phosphate. The transfer of this phosphoryl group from ATP to the hydroxy groups on carbon 6 of glucose is catalyzed by hexokinase. The next step is the isomerization of glucose 6-phosphate to fructose 6-phosphate. The reaction is a conversion of an aldose into a ketose. It is catalyzed by phosphoglucose isomerase and takes several steps because both glucose 6-phosphate and fructose 6-phosphate are present primarily in the cyclic forms. The enzyme must first open the 6-membered ring of glucose 6-phosphate, catalyze the isomerization, and then promote the formation of the 5-membered ring of fructose 6-phosphate. A second phosphorylation reaction. Fructose 6-phosphate is phosphorylated at the expense of ATP to fructose 1,6-bisphosphate. This reaction is catalyzed by phosphofructokinase. This enzyme plays a central role in the metabolism of many molecules in all parts of the body. Phosphorylation of the fructose 6-phosphate to fructose 1,6-bisphosphate prevents the reformation of glucose 6-phosphate. The newly formed fructose 1,6-bisphosphate is cleaved into glyceraldehyde 3-phosphate and dihydroxyacetyl completing stage 1 of glycolysis. This reaction is readily reversible and is catalyzed by aldolase. Glyceraldehyde 3-phosphate is on the direct pathway of glycolysis, whereas dihydroxyacetyl is not. Dihydroxyacetyl and the glyceraldehyde 3-phosphate are isomers that can be readily interconverted. The former is a ketose, the later is an aldose. The reaction is catalyzed by Charles phosphate isomerase. It is rapid and reversible. The reaction proceeds readily from dihydroxyacetyl to glyceraldehyde 3-phosphate because the subsequent reactions of glycolysis remove this product. So, in the first stage of glycolysis, the preceding steps have transformed one molecule of glucose into 2 molecules of glyceraldehyde 3-phosphate. But no energy has yet been extracted. On the contrary, thus far, 2 molecules of ATP have been invested. The second stage of glycolysis is a series of steps that harvest some of the energy contained in glyceraldehyde 3-phosphate as ATP. The initial reaction in this sequence is the conversion of glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. The product has a high phosphoryl transfer potential. One of its phosphoryl groups is transferred to ADP in the next step. The reaction is catalyzed by glyceraldehyde 3-phosphate dehydrogenase. The reaction can be viewed as the sum of 2 processes: the oxidation of the aldehyde to an carboxylic acid by NAD+, and the joining of carboxylic acid and orthophosphate to form the isophosphate product. 1,3-bisphosphoglycerate is an energy-rich molecule with a greater phosphoryl transfer potential than that of ATP. Thus, it can be used to power the synthesis of ATP from ADP. Phosphoglycerate kinase catalyzes the transfer of the phosphoryl group from the acyl phosphate of 1,3-bisphosphoglycerate to ADP. ATP and the 3-phosphoglycerate are the products. The formation of ATP in this manner is referred to as substrate-level phosphorylation. In the remaining steps of glycolysis, 3-phosphoglycerate is converted into pyruvate, and the second molecule of ATP is formed from ADP. The first reaction is a rearrangement. The position of the phosphoryl group shifts in the conversion of 3-phosphoglycerate into 2-phosphoglycerate. This reaction is catalyzed by phosphoglycerate mutate. Then the dehydration of 2-phosphoglycerate introduces a double bond, creating an anol. Anolase catalyzes the formation of the anol phosphate, phosphoanol pyruvate. The final reaction is the irreversible transfer of a phosphoryl group from phosphoanol pyruvate to ADP. It is catalyzed by pyruvate kinase. Thus, the glycolysis pathway is completed. This is the overall reaction of glycolysis. One molecule glucose is converted into 2 molecules pyruvate. The initial investment of 2 ATP per glucose in stage 1 and the subsequent generation of 4 ATP by substrate level phosphorylation in stage 2 give a net yield of 2 ATP per glucose. Glucose is oxidized to the extent that 2 NAD+ are reduced to 2 NADH, and NADH will be reoxidized to glycolysis to continue. Okay, that's all of glycolysis. Thank you.